Hello everyone, I hope everybody is fine. We continue talking about functions, and this time combination of functions. So if you have two functions, let's say y equals f of x and y equals g of x, then believe it or not, you can combine these functions. I mean, you can add them up, you can subtract them, you can multiply two functions, and you can actually divide two functions. So the sum function is defined as a f plus g of x, and that's how we write it. And that is nothing but the sum of the two functions, f of x plus g of x. And then the difference function is f minus g of x, which is nothing but f of x minus g of x. Obviously, g minus f of x and f minus g of x would be two different functions. And product function is fg of x, which is f of x times g of x by definition. And the quotient function, after the product function, it comes quotient function, is f over g of x, which is defined as f of x over g of x. Basically, you grab the two functions and divide them by one another. Needless to say that the denominator cannot equal to 0. Now, about the domain of these combined functions, domain of sum function, domain of difference and product function, what we can say is that the domain of the sum, difference, and product functions is actually the intersection of the two domains of the two functions, g of x and f of x. So this symbol here, it stands for intersection. So it says that the domain of product function, for example, is the intersection of the two domains of f of x and g of x. So basically, whatever the two domains are, whatever the two sets are, you have to take the common area, basically, the common interval, or the intersection of the two sets in order to find the domain of the product function. Same thing for domain of the sum and difference functions. Uh, Basically, the sum function and the difference function and product function are defined wherever actually both of these two functions f and g are defined. With respect to the quotient function, the domain is once again the intersection of the two domains, obviously, but then we have to subtract those values of x that cause the denominator to be 0. So we are saying domain of f over g equals domain of f, intersection of that with domain of g, but then minus the set of numbers like x belonging to the set of real numbers such that g of x is equal to 0. So whatever roots the denominator has, we have to actually deduct it from that intersection of the two domains. Okay, so this was just the basic definitions, and here are a few examples for you. F of x and g of x are both our square root functions here. F of x is square root of x minus 1, g of x is square root of x minus 2. We want to find domain of f plus g. Now, first of all, what is f plus g? Well, f plus g, the sum function, is going to be square root of x minus 1 plus square root of x minus 2. This will be the equation of the sum function. So f plus g of x equals square root of x minus 1 plus square root of x minus 2, the sum of two radicals. With regards to the domain, well, we know what the domain is. It should be the intersection of the two domains. So I'm going to find the domain of f, and domain of f clearly is values of x that are greater than or equal to 1, right? So we start from 1, comma, positive infinity. I write it in the interval notation. And domain of g would be similarly 2 comma positive infinity, and the domain of the sum function f plus g would be the intersection of these two domains. So one interval starts from 1 goes to infinity, the other one starts from 2 goes to infinity. For example, 1.5 is an element of the first domain, but 1.5 is not an element of the other domain. But we need to find that intersection of the two intervals. So what would be the intersection of these two intervals? Clearly, if x is greater than 2, automatically it would be greater than 1, obviously. So the answer would be 2 comma positive infinity. That is domain of the sum function. You can, of course, write it in set notation as all real numbers such that x is greater than or equal to 2. With regards to the quotient function, domain of f over g, well, we have to say the same thing, but the thing is that, uh, first of all, let's construct that f over g of x, which is f of x over g of x. That would be square root of x minus 1 over square root of x minus 2. Here, we see that at x equals 2, the denominator becomes 0. And we have to exclude this one single value from the intersection we had. So before we said that x can be greater than or equal to 2. And that was the intersection of the two domains. And we say the same thing for the domain of the quotient function, except that the value of 2 itself, that one single value, would be inadmissible for us. So we are going to say we are going to exclude the 2. So instead of using the closed interval, we're going to use the open interval 2 comma positive infinity. That will be the domain of f over g, or the quotient function. In terms of set notation, you can say all real numbers such that x is only and only greater than 2. That will be the domain of the quotient function. You see how delicate things are, very minor differences here and there. The product function, well, it is going to be fg of x, which would be square root of x minus 1 times x minus 2, because when you multiply two square roots, you just write one square root and you multiply the radicands. So you can say this is actually square root of x squared minus 3x plus 2, that quadratic trinomial under the radical sign. So this is actually the product function itself if you want to find its equation. But the domain is the same as what it was before, because we know that this domain of some difference product functions is always the same thing. So the domain of the product function is the same as domain of the sum function, which would be what we found earlier, x greater than or equal to 2. Okay, this is another example. We have a logarithmic function and we have a square root function. It says find the domain of f minus g. Now, first of all, f minus g of x would look like something like this. Log of x plus 5 minus square root of 3 minus x. So if I say this is a logarithmic function, I cannot say that because of the square root part. And if I say this is a square root function, again, I cannot say that because of the logarithmic part. So what this is actually the combination of two functions. What kind of functions? Square root function and logarithmic function. So this is the equation of the difference function, f minus g of x. But they're asking for the domain of that. So in order to do that, I have to find domain of f first of all, which is the domain of the logarithmic function. And we know that a domain would be all real numbers such that x is greater than -5. X equals -5 is the equation of the vertical asymptote for that function, as you very well know. So x has to be strictly greater than -5. And for the other function, domain of g, we are going to say that all real numbers such that the radicand is positive, which means that x has to be less than or equal to 3. So x is less than or equal to 3. In terms of interval notation, x larger than -5, excluding -5, would be something like this. It's an open interval. And in this case, we have a open interval of -infinity, comma, 3, and then it has to be closed interval with square brackets because it has to include the 3. So these are the two domains, but the domain of the difference function, we said that it's the intersection of the two domains. So I'm going to say d of f, d of g, and now d of f minus g is the intersection of this domain. So what is that set of numbers? What is that interval that has to be restricted to 3 from the right side and restricted to -5 from left-hand side? So we would say the intersection of domains d of f intersection with d of g should be -5, comma 3. So including 3, excluding -5, basically. Open interval -5 and 3, including 3. So this is the domain in interval notation, but we can also write this in set notation. So x is less than or equal to 3, but it's only greater than -5. So this would be the same the domain of difference function, but in set notation instead of interval notation. I'm just writing both because both are used a lot. So we found the domain of the difference. Now, just to show you, in order to visualize this business of intersection, so 1, 2, 3, 4, 5 is here, and 1, 2, 3, 4, 5 is here, -5. So that's -2. Now, the first function had a domain starting from -5, excluding -5, going all the way towards positive infinity. So this was the domain of the first function. I'm graphing the domain set just to visualize. And the other one, the other function had this domain ending at 3. So ending at 3, so that's a solid dot, and it's not an empty circle, and it goes all the way to the left-hand side towards negative infinity. So these are the two domains, the graphs of the two domain sets. Now, what is the intersection of these two? You see that the green one stops at -5. So we start at -5 right there, excluding -5, and we go all the way only up to 3. So I draw a solid dot there. So this red graph you see is the graph of the intersection of the two sets. In order to visualize, what the domain of the difference function is, it is this red part, okay? So this is the domain of f minus g, if you want to visualize it. The green one was the domain of function f, so this was domain of f, and the black one was the domain of g, which was stopping at 3. So this is domain of g. So domain of g, domain of f, and the intersection is right in the middle. They're asking for domain of f over g as well, so I'm going to try to quickly find that as well. So we already have the intersection. We just have to deduct the roots of the denominator. So f over g of x is the quotient function. It's going to be log of x plus 5 over square root of 3 minus x. And we know that the root of the denominator is specifically 3 only. So whatever the domain was, it was here, -5 up to 3, including 3, excluding -5. So I'm going to say domain of f over g equals all real numbers such that x is between -5 and 3, but this time I'm going to exclude 3 because that's the root of the denominator. That is what causes g of x to be 0. In interval notation, the answer would be -5, 3. It is an open interval. So this would be the domain of the quotient function. And domain of the difference function is the same thing, except that 3 is okay to be there. But here, for the quotient function, it is not okay for 3 to be part of the domain because it causes the denominator to be 0. So there's another question here. It says f of x and g of x are given. Find the product function. This one doesn't say anything about domain, or actually it says. So we're going to say fg of x, the product, is going to be f of x times g of x. So we are multiplying a linear function by a quadratic function, actually. So we have to perform the expanding thing. So we end up with 4x cubed if you multiply 2x by every single term inside the other brackets. So, and then we get 2x squared minus 6x plus 6x squared plus 3x minus 9 after you multiply 3 by the other terms. And when you wrap things up, 4x cubed plus 8x squared minus 3x minus 9 is the final answer. And you see that the product function here, fg of x, happens to be actually a cubic function here, because the product of a linear function and a quadratic function becomes a cubic function. And we know that the domain and the range of a cubic function is actually the set of real numbers in both cases. So domain and range of the product function as a cubic function in this case would both be actually the set of real numbers. A simple short question here. So in this lecture, we learned about combination of functions. We said that 4 ways you can combine functions: adding them, subtracting, multiplying, or dividing them. And we talked about the domain of these combinations of functions. And we did review some examples about how we find the domain of difference function or sum function or quotient function, so on and so forth. I hope by doing more practice questions, you will continue studying. And in the next lectures, I think we'll be talking about the graphs of these sum functions, difference and product functions, and so on and so forth. Thank you for your attention.